We have already learned that we can use integrals to find areas. If we were looking for the area underneath a curve, we could break that area up into rectangles, and we could sum the areas of these rectangles to get an approximation of the area under the curve. As we let those rectangles get thinner and thinner, we get closer to the exact area under the curve. I would like to use the same principle to find volumes. So suppose we didn't know how to find the volume of a sphere. Could we use that same technique to find the volume of a hemisphere? So what I'm going to do is I'm going to slice the volume of the hemisphere into cylindrical slices. So imagine that I sliced off the top of this hemisphere into a nice thin cylindrical slice. And then I made another slice like this, and then another slice like this. And I just keep chopping up this hemisphere into these thin cylindrical slices. Then what I could do is I could find the volume of each one of these slices, because that is the volume of a cylinder, and then add them all up so that I can get the total volume of this hemisphere. Now, of course, by slicing it horizontally, I am getting near cylindrical slices, but they're not perfectly cylindrical. So there's a little bit of the volume that I'm not capturing by assuming that these slices are cylinders. But as I make these slices thinner and thinner, I should be able to get to the exact volume of this hemisphere. Okay, so what we're going to do is we're going to approximate the volume by chopping the hemisphere into n thin horizontal circular discs at heights h sub I are equal to I delta h. And I can equal 1, 2, all the way through n. And delta h is the total radius divided by n. So each one of these slices is going to appear at some height. We'll call it, say, h sub 1, h sub 2, etc. So we can call a general one h sub I. And we're going to chop it up into n slices. And we know that the height of this hemisphere is r, so delta r, which is going to be the distance between slices, or the thickness of the slices, delta h is going to be r over n. Okay. So now that we've found these disks, we want to find the volume of each disk, and the volume of each disk is going to be pi times the radius of each disk, we'll call that r sub I squared, times delta h. But the volume of the disk is in terms of the radius r sub I, but the thickness is in terms of h. So it would be nice if I could relate r sub I, the radius, to the height of each disk. So imagine I have the radius of a disk. I'm going to call this r sub I for the radius of a disk. That disk is going to appear at some height. I'm going to call that height h sub I. And then I notice that these two distances, r sub I and h sub I, are related by a right triangle with hypotenuse capital R, which is the hemisphere of radius r. And so r sub I squared plus h sub I squared equals capital R squared. Or r sub I is equal to the square root of capital R squared minus h sub I squared. And that gives me a relationship between r sub I, the radius of the ith disk, and h sub I, the height of that disk. And so now I can rewrite the volume of each disk as pi times r sub I squared, so r squared minus h sub I squared delta h. And so now I have the volume of each one of these disks in terms of the height of that disk. So that the total approximation of the volume of the hemisphere is going to be the sum from I equals 1 to n of the volumes of the disks. So the sum of pi times r squared minus h sub I squared delta h. And now we have to ask ourselves, what kind of sum does this look like? I essentially have a function of h, you could call it f of h sub I, times delta h. And so in fact, this looks like a Riemann sum. Well, with Riemann sums, we know we can improve our estimate by increasing the number of disks that we use. So we can increase n, or we could actually decrease our delta h. And of course, those two things are related because delta h is equal to r over capital N. Okay. So we can find the true volume by taking the limit as n goes to infinity. So the limit as n goes to infinity gives us infinitely thin disks or cylinders. And because we're using those infinitely thin cylinders, then when we add up all of those infinitely thin cylinders, we'll get the exact volume of the hemisphere. So this is going to be the limit as n goes to infinity, the sum from I equals 1 to n of pi times r squared minus h sub I squared delta h. And that limit is going to be the integral of pi r squared minus h squared dh. And we're going to integrate from 0 to r, because we're integrating through the possible heights, and the height of the lowest disk is going to be at height 0, and then the highest disk is going to be at height r. So now all that's left is to compute this integral. So we have pi times r squared h minus 1/3 h cubed. All that is evaluated between 0 and capital R. So we're going to get pi times r cubed minus 1/3 r cubed. So that looks like 2/3 pi r cubed. And if you remember your formula for the volume of a sphere, that's 4/3 pi r cubed. And so this is a hemisphere, so that is half of the sphere. And so this is our technique for finding the volume of a solid. We're going to want to break that volume up into pieces, into disks. We're going to slice through that volume, and then we want to find the area of each one of those, the volume of each one of those slices, and then we want to add up those volumes of slices to get an approximation of the total volume. Of course, if we use infinitely many slices, then that will give us the exact volume. Okay. Let's try the same technique for the volume of a pyramid. So what I want to do is I want to slice up this pyramid into horizontally into slabs. So imagining I'm going to slice across this pyramid in this horizontal direction, and what that's going to do is going to give me a thin slab. And that thin slab is going to have a square base because the pyramid has a square base, okay? And then it's going to have some sort of height. We'll call that height delta H. And so I'm not going to do this in the picture right now, but you could keep slicing this pyramid, and each one of the slices has a square base and has a thickness of delta H. So in essence, we can say that the volume of each one of these slabs is going to be the side length for the square base, S sub I squared, so that's going to be the area of a square, times delta H. So again, I have the volume in terms of kind of two variables, the side length of my square, which I'll call S sub I, and then the thickness, delta H. So I'd like everything in terms of H. So I need to, again, form a relationship. And so what I'm going to do when I do the volume of this pyramid is actually I'm going to think about it kind of upside down. So that 0 is actually at the top of the pyramid, and then the height, capital H, is at the bottom of the pyramid. And then I want to go ahead and look at a particular height, and that height is going to be H sub I. So that this distance right here is H sub I. And then half of this distance on the base is S sub I over 2, and then the other half is S sub I over 2. Well, I'm going to extend this all the way down so that half of the base is capital S over 2, and then the other half of the base is capital S over 2. And we know that the height is capital H. So I want to form a relationship between S sub I and H sub I. So the way that we're going to do that is we're going to look at using similar triangles. So I'm going to look at this triangle, which is a right triangle, and I'm going to compare it to this triangle. Okay. So we can say that the base of the triangle, which is S sub I over 2, divided by the height of that triangle, H sub I, is equal to the purple triangle's base, S over 2, divided by capital H. Now hopefully you notice that these 2's will cancel. And this gives us the relationship that we were looking for, that S sub I is equal to S over capital H times H sub I. So now I've related my side length of my square base to the height at which that slice appears. So the volume of the slab is going to be capital S squared over H squared times S sub I squared, or sorry, H sub I squared. So that's squaring the sides so that we get the area of the square base, okay, delta H. And so the volume of the pyramid, well, that's going to be approximately the sum from I equals 1 to n, s squared over h squared times h sub I squared delta h. And now, if we let n go to infinity, then that actually equals an integral. The integral ranges over the h's, so 0 to capital H, s squared over h squared times h squared dh. And then we can evaluate this integral. So capital S squared over h squared times 1/3 small h cubed evaluated between 0 and h. And then if we plug that in, we're going to get a 1/3 capital S squared h cubed over h squared, or h. And so that is the volume of the pyramid with a square base. So again, the idea is we're going to take this solid, we're going to slice it into thin slices, and we're going to find the volume of those thin slices. We're going to add them all up and then recognize that that sum, if we let the slices get thinner and thinner, essentially using an infinite number of slices, that becomes an integral that we can evaluate. And now we know how to find the volume of a pyramid as well as the volume of a hemisphere.